How does a photoreceptor work? Not it. So wait, I'm going to go way back here. I'm going to draw this way over here on the side. Okay. Just so we can, I'm just going to draw it so that we can get a little bit of frame of reference. I'm just going to draw a rod. The cones are very similar. Okay. A little physics. What color is my shirt? How do you make blue?
Witchcraft.
Magic. Okay, moving on. But how do you make blue? How do you make red? How do you make black? Or white? You find a certain material that reflects a certain kind of light. Okay? So this is actually really cool. If you ever have to take physics, it does help you understand psychology better, because our brains are physics machines. So I'm going to draw a surface of a blue molecule. Okay? And when the blue, okay, so how does light work? Sorry, physics. So light, just picture light coming in as a wave. Okay, it's actually a little packet, and the packet vibrates back and forth. The faster it vibrates, the purpler it is. Okay, the slower it vibrates, the redder it is. Till it gets too slow, then it just becomes heat, and you can't see it, but can you feel it? But if I turn up the speed a little faster, and it gets to purple, then it becomes violet, which is very violent purple, and then what does it become? Ultraviolet. And what does it do to your skin? Burns it. So when the frequencies are just right, so I want you to think of this as the frequency of this little guy, this little this photon coming in. If the frequency is just right, it lands in the bottom of the molecule, of the blue molecule. Okay, if the frequency is just right, it lands on the bottom, and if it lands right at the bottom, it goes shooting back out. It's a little blue photon, which I'm drawing not in blue, but this won't change to blue. So, and thank you. I think all those pictures make it a little bit too big, and it hurts the RAM. Hi, Freud. Okay, yeah.
So this is kind of a strange question. Is that why when your skin when you get really cold, kind of like frostbite, when your skin kind of turns kind of purplish?
That's because that's nothing to do with the pigmenties. What that has to do with when your blood is if you look at the veins on the top of my hand, some of them are purple. That's because that blood has been used already, and there's no oxygen left in it. I mean, that blood is already going down all the way to my fingers, and my muscles have used all the oxygen. And so now, where are the purple ones going? Well, you can actually see it. You just do this. They're going that way. It's fun to do. If you're ever bored in class, you can just... my blood pressure is relatively low, so I'm like watching it. It's like, you can actually see the blood flowing back. So, but if you cut yourself, what color is blood? Red, because as soon as the hemoglobins hit oxygen, they turn red. Because when the oxygen's in the hemoglobin molecule, it fills it up, and when it gets stretched out, it reflects what color? Red. When it's not filled, it's crinkly, and it only reflects purpley blue color. That particular wavelength. So, is this shirt pure blue? No, so the pigments aren't exactly perfect. Your jacket is much better blue than my shirt is blue, because it has a much more consistent color, so the pigment is much better. When you look at, what are things that are really perfect colors? What kind of things make really perfect colors? Well, not nature. I'm thinking nature produces some really nice colors, but they're not perfect. They're scattery. That's what kind of makes them pleasing. Like the computer generated palette, when I pull up the marker, okay, these colors are relatively exact. In fact, there's a computer code that if you zoom in, if I can still put my glasses again. Anyway, if I zoom in enough on these, what is each one of these little pixels on here? The computer won't let me zoom all the way in. But if I zoom all the way in on this, you can actually see each pixel. See the square edges? So each dot is made out of 3 basic colors. Each dot is made out of these yellow, red, and blue, or cyan, whatever it is. Okay? And when I'm mixing those colors in each one of those little dots, by mixing those colors, these are mostly, what color? Well, green's not one of the primary colors, so it is technically, but it's mostly yellow and blue. Because if I mix yellow and blue together, what do I get? Green. So what's interesting is that, going back out of my eyeball, okay, so the photopigments respond to when a light molecule hits them in just the right spot, they activate the G proteins. They activate the second messenger systems. If the light molecule, if I draw a red one here, or a slightly purplish one, and it's coming through, and it hits on the point, it's going to bounce off to the side. So we say it's going to absorb. You can't even see that. There you can see it. So if I draw this purpley one here, it's going to hit, and it's not hitting in the little pocket, it's going to bounce off one way or the other. So when the light bounces off, we say it doesn't reflect that color. So what is something that is black? Don't look around for something that is black, but what is black? Like, why is the board black? It's not the absence of color. Light's not reflecting off of it. So when light hits it and doesn't reflect back, we see it as black or dark. But now, even though this is black, how come it's not as black as this black, which is white? Because the projector is still shining light on it, because that's how it works. And even though if it's shining a black light, it's still lighter than a black surface. So what our eyeballs are doing is the photopigments inside of each of these little discs, inside of each little photoreceptor, are absorbing light molecules. When the light molecule hits that particular receptor, it bounces back and you can, quote, see that color. The thing is, we only have 3 basic colors that we see. We only see 3 basic colors. How can we see the beauty in this octopus eyeball if we only see 3 basic colors? Good morning. We have a couple million megapixel camera in our eyeballs. Multi-megapixel camera. So we can see if one is seeing red and the one right next to it is seeing orange or blue, the combination of those two can make almost an infinite number of colors. That's why, what do they call the displays on Macs? Retinal displays. Because Mac, ever since Mac first came out, they prided themselves with using lots of dots to make stuff. We have a Mac monitor on my old computer in my office. It's beautiful because they make very high resolution monitors. Because when you look at it, it's pretty. And you don't seem to notice that it doesn't work as well because it's pretty. You have to talk nice to it, otherwise it crashes. You're a nice computer. Good job, Mac. You're so beautiful. And the computer just works. My wife destroys her computer. It still just works. Doesn't look pretty without the anti-glare coatings halfway off of it, but that's okay. So, what kind of photoreceptors see color? Cones. Okay, good morning. That purple is absolutely terrible, unless I make it thick. Okay, why is the purple terrible? Okay, so the relative contrast between the black and the purple is not good. We actually see contrast in light and dark. Contrast in light and dark. And so what we start to see is what we call receptive fields. A receptive field is an area in your brain, in your retina, that is responsive to certain lights. So when the photopigment is activated, the cell does what? I'm going to get rid of the purple, sorry. What does the cell do when we turn on the light? So here's the cell in the dark. Diggy, 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 diggy. Photopigment is activated. What does it do? Slows down. Lights back on. Changes relative firing rate. What if you're in a steady light environment? What do you think your eyeball does? Dark, and now it's in the dark. It doesn't stay the same, it slows down. When it slows down, and then I shine a light, I can see contrast. Could you see this edge right here before? No. And if we flick the lights back on again, can you flick the lights back on again? What happened? Oh, you can still see the edge. Yeah, you can still see it. But the longer we're sitting here, what happens with your ability to see the edge? It looks like it's getting better to me. Once your eyeballs adjust, you can start to see things better. How come you can't see the light purple line up here anymore? There's not enough photoreceptors activated by that purple color for you to decide where the edge of the purple is and where the edge of the black is until I zoom way in on it. Is it easy to see now? Because now it activates a lot more photoreceptors. More photoreceptors are activated, so you can easily see the relative space between the lines. And this is all about receptive fields. If I zoom way out, is there any purple there? I can see a little bit. Can you see where you can see? I can see it. I don't know where you can. Right here. I can barely see that, but I can see right. Why would I be able to see it here, but not up there? It's next to the white. And when you're activating the white neurons, then you're able to see the different colors better. We only see things in relative. We don't see things in absolutes. We assume that the world is how we see it, but we don't. It's not really how we see it, because what we're seeing are receptive fields. I'm not going to go into the different types of receptive fields. I don't think that's necessary for you guys in this class right now, but just some people like to know exactly why. But there are different kinds of receptive fields. And the different kinds of receptive fields see different patterns of things. So this is what a receptive field looks like. We have tons and tons of photoreceptors. And there's tons and tons. What are these purple ones? Ganglion cells. Okay, so anyway, what are they called? Okay, now, so what's in between the two? Bipolar cells are in between the two. Okay? So I'm just going to draw this really quickly. Here's a photoreceptor. Here's a bipolar cell. Here's a ganglion cell. So now I'm going to draw some dendrites from my ganglion cell. And then I'm going to draw a bunch of, what are these? Bipolar cells. And a bunch of badly drawn photoreceptors. So I'm going to shift colors. Okay, shifting colors. I'm going to draw the next ganglion cell right here. And what does it have associated with it? A much thicker line is what I'm seeing, but that's not important. So again, a bunch of dendrites going out. So far, so good? Do you see what I'm looking at? So what I just drew was 2 of these. Thousands. Or millions, probably. Well, we'll talk about the density and the different pathways coming up in just a second. But, so now, what's interesting is there are other neurons inside here, which I'm going to change this rainbow fancy one to green. Okay? There are neurons that go back and forth between rods and cones. These are called horizontal cells. So far, so good. Horizontal cells go laterally amongst, picture this as a three-dimensional disk. They're going back and forth between the cells across the receptive field. Okay? So now, what happens is if I shine light on both of these receptive fields, I shine light on both of these receptive fields. Okay? So a light is shining and it's wide enough, like this right here is wide enough to hit multiple receptive fields. This ganglion cell is going to fire, and this ganglion cell is going to fire. These are going to stop firing, these are going to start firing, this is going to fire. So if light is shining on both of them, both receptive fields are fired. Okay? I've got to figure out a way to draw this with being effective. So let's say, here's my light beam coming in, and it lands like this. So what is it doing relative to the 2 receptive fields? It's activating this receptive field and activating more of this receptive field. So how do you see the edge of something? How do you see where the edge of something is? Right. So I'm going to draw it like this. 1 receptive field, 2 receptive fields, 3 receptive fields, 4 receptive fields. I got 2 out of 4, not too bad. So if the light is shining here, where's the edge? What does your brain see? This is the light right here. Where's the edge? Okay, what does a receptive field do? You can do this. I know you can. If I activate anything in that receptive field, what do you perceive? Light. So if I see light here and I activate this one, you see light that is this wide. So is this one seeing any light? No. So where's the edge? In between these 2 receptive fields. You see that? So you don't actually see each photon. You don't see each cell being activated. What you see is each receptive field being activated. So this is the edge of the boundary right here. The light is shining here, the light is not shining here. So therefore these photoreceptors in these receptive fields are firing, these aren't. But why is this a perfectly nice fine edge? Ooh, science. Can I mess with this nice fine edge? Can I spread this line out? I can't really spread that line out, but I can definitely spread this line out. This is a really nice line. Why is this such a nice line? High contrast. There's a lot of light activation here, a lot of light activation here, no light activation here. This looks blacker than this. Same color. But it looks blacker because contrast. So if I go like this, wrong one. I want this one. Well, I got better. Oh, now it's blurry. There we go. Now we're talking. So if you take off your glasses, is it better? No. So it actually gets worse if you take off your glasses. So now what's wrong? It hurts because your eyes are moving back and forth trying to find the edge. So the blurriness, or Gaussian blur, what I do is I take the edge pixels and I blur them. So now what happens is this is not activating one receptive field, it's activating a sum of this one. Some of this one, some of this one. And so what happens, your eyeball keeps moving back and forth or flexing its muscles trying to bend your lens so it hits the receptive fields, or they slowly just close. Hi. You're out there for a second. It must have been very peaceful. Okay, I love that feeling, especially when I'm watching golf. I hate golf, but I watch it because it's a good nap. Oh, too far. How's that? One more. That's pretty good. Okay, so science. You need a ruler. Okay, so now that I brought this back into good focus, and I can hit the computer, it can autofocus. How does a computer autofocus? Well, it shines a light on the board, and the light reflects back to a sensor there. If it can find the edge of something, it can tell you whether it's in focus or not. And this is how has anybody ever had the auto eyeball sensor done with their eye? You put your face in the machine, and it goes and it automatically tells you what your prescription is. It is neat. It does the same way the projector does. It looks at the light being shined on the back of your eyeball and adjusts the focal length until they see the light being shined properly on the back of your eyeball. Once it's shined properly on the back of your eyeball, it says, close enough. Well, and how do they do it with the eye doctor? What they do is they have lenses that are slightly different, rotating this way and rotating this, the thickness and rotation. And then they get the thickness close, and then they slowly adjust it by little increments till you can see things better. It's really kind of fun. 1 or 2, I can't tell. Go back. 1 or 2, go back. They're the same. Well, sometimes they are the same because sometimes the differences are so small that you can't perceive a difference. In other words, it doesn't change which photoreceptors it's lining up on. So if you have bad vision, I think I drew this somewhere on here. I think it crashed though when I was recording it. I think it did crash as I was recording it, so it didn't stay. But if you look at the back of your, oh yeah, I do it over here. That's right. There it is. Okay, if you look at the back of your eyeballs, this is what the receptive fields look like. In your fovea vision, where all your eyeballs should be focused, what do you have? Little tiny, not a lot of receptors, a lot of receptive fields, a lot of ganglion cells. Because there's a lot of ganglion cells, if I shine a light, brace yourself, because we're starting to see things. If I shine a light, I will shine a shadow that is like this. Okay? If I shine a shadow like this, what does my brain see? That receptive field activated, that one not. Is this one activated? This one right now, this one right here? No. That one, yes. This one, no. So as I go down, all these receptive fields are activated. All the ones where the line is are activated. All the ones where the line isn't are not activated by this particular line. Yeah.
Like, is that just a demonstration? Because I'm thinking about like how light goes into your eye. And like, wouldn't it just be like a direct hit the fovea? Or
Well, but if you sit and just look at the board, okay, in order to really understand this, we have to use this. We have to use this experiment. And I just like this for a long time. Oops, sorry.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat.
I want to get the copyright infringements. Well, it's a really groundbreaking thing. So if I put that line across the screen again and move it down, when I do that, there's a single neuron in your brain going, ooh, me, me. And what does that mean? Choose three, son. Choose three. Okay, sorry. That's what the character was. Okay, so as it moves across the cat's retina, one cell responds to diagonal right down. Okay. One single cell responds to any sort of receptive fields that are lined up in a particular angle. Following this? So if I put a line across anywhere in the retina at this same angle, that one cell fires. So what you're actually seeing is the relative firing of receptive fields in your eye. The relative firing of receptive fields in your eye. So if I turn it just a little bit, that cell we were listening to is not going to fire. But what do you think is going to fire? Another cell. And so the way your retina actually projects into your brain, I'm going to roll over here, is, well, I'm just going to pull up a picture because it's too hard for me to draw.